Today we're going to talk about 5 myths of elastomer material datasheets. If you have any questions during the course of the presentation, feel free to post them as we go along and I will try to answer them during the Q&A session at the end. Before we start, I'd like to introduce myself. I'm Chris Allen and I'm the Oil and Gas Product Manager here at Precision Polymer Engineering, PPE. Whilst working for an oil and gas equipment provider many years ago, specialising in the design and development of subsea marine connectors and pipeline handling tools, I attended a sealing training course, and it sparked my interest in elastomers after coming to the stark realisation that sealing with O-rings is not as simple as picking up a catalogue and selecting a rubber ring. After all, how difficult can it be when there are only 2 dimensions to define it? Elastomers are a weird and wonderful material, and unlike most other materials that we come across every day in engineering. I've been with the business for 8 years now, having spent the first 7 years as the application engineering manager with a focus on the oil and gas industry, having overcome many challenges in providing and qualifying solutions to meet the needs of the industry. So how do you use datasheets? And what do they tell you? How do you use that information that they tell you? What do they not tell you, more importantly? What do you need to know in order to be able to specify or select a material? How useful are these material datasheets? And what are these myths and misconceptions that we will talk about? So these 5 myths or misconceptions that we're going to talk about today, they're around physical properties of materials, the high temperatures that you see stated on a datasheet, the low temperatures that you see stated, these industry approvals, many of them that we see in the oil and gas industry, what do they mean? How do they affect it? And chemical resistance. What do we mean by chemical resistance? So, here we have some examples of datasheets. These can be found on the internet and in various brochures from various suppliers. As you can see, they all contain a table with numbers, values, and these are usually accompanied by some text. Generally speaking, people tend to focus on the numbers found in the tables, but more often than not, these values are very generic. Usually you get more information from the text. You'll find information of where the material may be good at, which particular applications, which particular products. Effectively, the text will sing the praise of the material. When looking at numbers on the datasheet, as I've mentioned, they are often quite generic. For example, if you look at the hardness for a material, more often than not it will be a 90 Shore, a 70 Shore, maybe a 75 Shore, maybe even 80. But you'd never see an 82.3 or an 85.6. This is because the tolerance and the variation through testing gives a wide band, typically plus or minus 5 hardness points. Not only is the tolerance band wide, but also the tests are inconsistent. So testing the same sample in various places, or even in the same place time after time, will give you different results. This is very different compared to the metallic world. As an engineer, when I see round numbers and numbers that regularly repeat themselves, you have to start questioning why that is. Typically in engineering, we rarely deal with round numbers or regular numbers other than maybe pi and log e. Here we have a typical elastomeric material datasheet. The datasheet defines the grade of material and what type of material this is. In this case, it's a low temperature ED resistant perfluoroelastomer called G90LT. Often on a datasheet there will be a description of the material and an area giving key attributes, so where the material is good at, what are its key points, what are its unique selling points. It may also provide an area with typical applications or products that the material has been used in or is good for, or what the material has been developed for. Datasheets may also provide some alternate material grades which may be suitable as well. In this case, there is a small area at the bottom where some chemical immersion testing has been carried out and there is some information around that. But on all datasheets there will be a table full of numbers with various properties. This table with these values, although they are correct, they are often misunderstood. Tests that are carried out to determine these values are often carried out under laboratory conditions at very specific temperatures for very specific time periods and under very controlled methods. usually to an ASTM or ISO standard. This is a bit of a double-edged sword. On the plus side, you know that these tables with the values are consistent. They've been generated consistently from one test laboratory to another. However, are they actually relevant to your application? Your application isn't in a laboratory, it's probably not at 22 degrees C, and it's probably not only carried out for a few hours. So what does the datasheet not tell you? Well, it doesn't tell you what the physical properties of the material are like under the application conditions. The properties are listed as a single value, yet the material is non-linear. This goes for all of its properties. How do these properties evolve due to the chemical interactions, temperature, time? What are the properties that are influenced by other variables, such as the design of the seal, the design of the hardware, how the hardware interacts with the seal? This will define its stretch, its squeeze, its gland fill. What about the pressure? Is it high pressure, low pressure? How does that affect it? In fact, is the pressure cycling? Is the temperature cycling? Do we have high temperature, low pressure, low temperature, high pressure? These will all have an influence that will change the material's properties over time. Any industry standards or approvals that the material has been subjected to, if anybody's ever read any of these standards, you will notice that there are variables that can be selected, and therefore one material that's been tested to standard versus another material, they could actually have two completely different tests yet have the same approval. Ultimately, it doesn't tell you whether the material is fit for your application or product. So, what I would suggest, when using a datasheet, use it as a tool to help guide you and define whether that material is a candidate that may be suitable or not for your application. Once you've got a short list of materials, then the hard work really starts. Personally speaking, I would suggest reading between the lines. As you get used to using these data sheets, think about what information is missing or what's different to what you expect. For example, if you see an FFKM material that has compression sets tested on it, you'll notice that typically it's 70 or 72 hours at 200 degrees C. If you see an FFKM material that may be at 24 hours or at a lower temperature, alarm bells should start ringing. At shorter times or lower temperatures, it would suggest that the material has got poor compression set properties when compared to other FFKM materials. So what do you need to know? Well, ultimately, you need to know enough about the material so that you can make an informed decision as to whether the material is fit for purpose for your application or product. As mentioned before, typically you'll just use this as a guide to see whether it's a suitable candidate. Before making that decision, you need to know whether you have enough information to make it. So, if you don't, well, what information is missing? What information would you expect to see? If you would expect to see something in particular with regards to that material, but it's not there, it might suggest that that material's results for that particular aspect is not favourable. Are the test criteria relevant to your application? Are you comparing apples with apples? As mentioned before, if you have an FFKM and one is tested 72 hours at 200 degrees C versus another that's 24 hours at 200 degrees C, you have two different tests, therefore two results, and you're comparing apples with pears. What might be the failure mode of this material if it were to be used? This is an important consideration. If you understand what potential failure modes are likely to occur in your application or your product, that might lead you down the direction as to what information you need to be looking for that particular material to overcome those failure modes. As a simple example, if it were a high pressure application, typically we would be looking for a high strength, high hardness material so that it can withstand the forces exerted by the pressure to prevent extrusion. So here we are at the first myth or misconception, and this is around the physical properties. These are generated in a laboratory under very specific conditions. As you can see in the first chart on the left hand side, the tensile properties of a material have been generated at 22 degrees represented by the red line and at 125 degrees represented by the blue line. The two red dots show the data points which are used to define the tensile strength, elongation at break and modulus at 100%, which are used on the datasheet. As you can see, the tensile strength of the material at 125 degrees is significantly different to that at 22 degrees. These materials are highly nonlinear and are influenced by time and temperature as well as chemistry. In the second graph, we can see the evolution of the tensile strength of a material over time at 4 different temperatures. The higher the temperature, the faster the degradation of the material. In the third graph, we are seeing the influence of time, or the time dependency of a material as we pull it. In this case, a dumbbell has been stretched to 20% strain at 3 different rates. The slower we pull the material, the less force is required to pull it. As you can see there are 3 different speeds. We have 0.15 of a millimeter per millimeter per second, going down to 0.001 millimeters per millimeter per second, with a big variation on the force required. Because of this non-linearity, it means that there are no formulas for ascertaining performance or safety levels. What do I mean by this? Well, there isn't a formula where we can simply plug in the values and generate an answer. Also, FEA becomes a very complex and deep subject. The results are often directional and not factual. We can see a similar scenario for compression set. Here we have material A and material B with 2 values for compression set as reported on the datasheet. Now, generally speaking, the lower the number for compression set, the better the material in that respect. So as I look at this now, and I look at these datasheets that might say material A has compression set of 20%, and material B has compression set of around 31–32%, naturally speaking, material A would be a better material. However, when we plot the evolution of compression set over time, we can see that material B, although has an initial higher compression set compared to material A, it actually levels off. So over a number of days and weeks, you can see that the value hardly changes. In fact, it stabilizes at around 35–36%. Material A, on the other hand, continues to degrade even after a number of weeks. In this case, material B would be the preferred choice. This brings us on to our second myth or misconception, and that is around the maximum temperature rating as reported for a given material on a datasheet. What does this temperature actually mean? Well, it certainly doesn't mean to say the products will last forever at that temperature but fail 1 degree above. This temperature should be used for a guide. Generally speaking, materials fail due to chemistry and chemical reactions, and for every 10 degrees C increase in temperature, the rate at which those chemical interactions occur doubles. So for every 10 degrees C increase, we will halve the life of a seal. So try to avoid working at these maximum temperature limits. For example, if your application calls for a material to work at 150 degrees C, and you want to use a HMBR, I would suggest that you opt for a HMBR with the higher temperature rating of 180 degrees C rather than one that's rated to 150. Another consideration, especially with high temperature materials, is its coefficient of thermal expansion. As you can see, the FEA images on the left show massive difference between an FKM at 200 degrees C versus an FFKM at 200 degrees C due to the higher rate of thermal expansion combined with the elevated temperature. Think of it like driving a car. If we use a material at its upper operating temperature consistently, we're going to shorten its life dramatically. Likewise, when we drive cars, we tend to change gear at maybe 2–2,500 RPMs, even though the engine can comfortably go to maybe 6,000–7,000 RPMs. If we were to change gear at 6,000 RPMs, redlining it all the time, the engine, as you may suspect, will not last very long. At the opposite end of the spectrum, we have myth number 3, and that's around the minimum temperature rating for a material. Again, this should be used for guidance. The material is not guaranteed to perform at that minimum temperature, as there are many variables that will affect it. The minimum temperature is often based upon a number of tests, followed by judgment and experience. There are many variables that will affect the performance of a seal at these low temperatures. The design of the seal in combination with the hardware design, thermal cycling, how pressure is applied, the media and time will all have an influence. In a similar way that the CTE will increase the volume of material as temperature increases, when temperature decreases, the material will contract, reducing the volume. This has a knock-on effect in terms of its design and performance by the sheer fact that the squeeze is reduced. When the temperature does reduce in application, the material does not go from a rubbery material to a brittle material instantaneously. It goes through phase changes, just like water. As we all know, water freezes at 0 degrees C. However, when we chill water down to that temperature, we have a combination of water and ice. It is not fully solid. We have a similar scenario with elastomers, that as we chill it down to its glass transition temperature, the material will exhibit both brittle properties and also elastomeric properties. This is why the material can be used at a temperature below its glass transition within reason. This goes back to the judgment and experience of the manufacturer of the material. This reaction or change in phase is fully reversible. There is no harm done when the material transitions from a rubbery elastomeric material down to a brittle material and vice versa. We come to our fourth myth or misconception, and that's around the industry approvals and the testing. These should be treated as a point of reference to basically decide if this material is a candidate for the solution or not. Treat them as a benchmark. This should be listed as the bare minimum that the material can do. There are a wide variety of approvals and test standards, and this adds to the confusion in deciding which is relevant to the application. The criteria and methods can be vague or open to interpretation. Before deciding on which industry approval is relevant to your application, it's worth taking a moment to read through them, understand them, and make sure that they are relevant. And if there are any changes that you wish to do, speak to your supplier about it. Here we have a selection of the most common rapid gas decompression standards that are used within the oil and gas industry. And by far the most common that's referenced is the NORSOC M710, especially revision 2. As you can see, within Rev 2 we have a number of options with respect to the temperature and pressure. So we have 100, 150 and 200 degrees C, and we have 15, 20 and 30 megapascals. Guess which conditions your supplier uses to pass the material to NORSOC M710? That's right, it's 100 degrees C and 15 megapascals. Why? It's the easiest one. It gets the tick in the box. However, is that relevant to your application? In the latest revision of M710, Rev 3, it basically states, see ISO 23936-2. Within this standard there are a number of changes. So we now introduce an option for 2 different gas mixtures. We've reduced the compression from 20% to 14.5%. What's the influence of that? I'll tell you, it makes passing the test a little bit easier. Under high compression, tensile stresses are much higher within the sample and therefore it exacerbates the ED results. As you can see though, across these 6 industry standards, there are many different variations, all reporting the same theme, and that is the resistance to rapid gas decompression. Be careful when selecting a material. Make sure that the approval is relevant. If the material hasn't got that approval, ask your supplier about it. An even bigger minefield is the heat aging testing. So here we have 7 common ones that are used within the oil and gas industry. Now then, please note, I've referenced this as heat aging, but you guys might know it more commonly as sour aging or sour gas testing. But In most of these, there are options for both sweet conditions and sour conditions. Rarely are we asked for sweet conditions. Again, the most common one is probably the Norsoc M710 Revision 2 Annex A. This is done with 2% H2S. But is it really 2% H2S? If we look at the details for the media, we can see there are three phases. There is a gas phase, an oil phase, and water phase. The gas phase occupies 30% of the volume of the pressure vessel. The oil phase occupies 60%, while the water phase occupies 10%. Now then, the gas phase is composed of 2% H2S, 3% CO2, and 95% methane. The oil phase is composed of 70% heptane, 20% cyclohexane, and 10% toluene, while the remaining 10% water phase is 100% distilled water. In reality, the 2% H2S is much less when we look at the detail. Although most of the criteria are fully defined for the Norsoc M710 testing, the biggest influencer in this whole test is the temperature. Yet here we have the option to select our own temperatures, and we must select 3. Given the conditions, the temperature can be the make or break of that material with respect to it passing the testing. As noted before, for every 10 degrees C increase in temperature, we double the rate of chemical reactions. Therefore, if we reduce the temperature, we slow the chemical reactions down, and they can be slowed down sufficient enough to pass the test, almost irrespective of what material goes into it. Similar to the RGD, M710 Revision 3 now states to see ISO 23936-2. Here we now introduce options for the gas composition. One is at 2% H2S, and another option is 10% H2S. But again, it's a 30% gas phase, 60% oil phase, and a 10% water phase. Within this new ISO standard, there are 9 temperature ranges from which the material supplier can choose from, and these vary from the minimum option, which is 36, 51 and 66 degrees, to a maximum of 195, 210 and 225 degrees C. Another common heat aging selection is the API6A. Quite often materials are done to either DDEE classification or FFHH. There is a big discrepancy with this test method in the sense that the oil phase composition is down to supplier discretion. This can have a huge influence in terms of the performance of the material in these conditions. This is something that I will touch on later on. But essentially, some materials perform with some hydrocarbons better than other hydrocarbons. For example, HMBr and nitriles are not good with toluene. If we remove toluene from the equation, it means it's not an influence. If toluene is not present in the application, that can be a good thing. In a similar vein, you can discredit a material unnecessarily by selecting inappropriate hydrocarbons for the testing. Overall, when looking at this test matrix, as you can see, it is a minefield. If you need advice, speak to your supplier. They should be able to guide you through this. In many heat aging tests, the Arrhenius equation is used to try and ascertain a lifetime prediction. Great caution should be exercised when using Arrhenius. More often than not, a single property is selected and is measured in terms of degradation at a temperature over time. Typically, this is the tensile strength. However, when was the last time you saw a failure mode that was directly due to degradation or loss of tensile strength? In this example, we're going to look at boiling an egg. So, to boil an egg so that it has a hard white and a runny yolk takes approximately 6 minutes at 100 degrees C. At 90 degrees C, it would take around 8 minutes. At 80 degrees C, it would take around 10 to 11 minutes. Following the Arrhenius methodology, we should be able to predict how long it would take to boil an egg at 50 degrees C. In reality, we would never achieve this at 50. This is because the activation energy for the proteins within the egg are much higher than 50 degrees C, typically around 63. In the image you can see an egg after 1 hour at 65. We would have a similar scenario with elastomeric materials, as the chemistry that is occurring in the environment between the material and the application conditions is very complex, with different elements all having different activation energies. Therefore, Arrhenius would not work. Speaking of chemistry, let's look at myth number 5, chemical resistance. Datasheets provide little to no information regarding the material's performance in the media that the application would provide. Some immersion data may be present, but this is usually based on an ASTM automotive requirement, which is not necessarily relevant to your application, nor are the temperatures and the durations. How will this media affect the material? What kind of chemical resistance are we talking about? Is it resistance to swell, or is it resistance to physical attack? Will this actually present a failure mode? In the images on the left hand side, we can see the difference between swell and attack. Swell, in some cases, can actually enhance sealing. Attack, as you can see, is a physical and aggressive interaction between the chemistry and the elastomer. Chemical attack may present itself as embrittlement of the material, meaning that the material loses its elastomeric properties and goes brittle, and that behaves similar to a hard plastic. In effect, sealing force is lost. Let's take the humble rubber band as an example. If we place one in a plastic bag and in a drawer and left it for a few weeks, it is likely to still work. If we take an elastic band and leave it on a windowsill, after a few weeks it's likely to fail when we stretch it. This is because it's been exposed to UV light and air. The UV light provides a degrading effect on the material and starts to break down the chemical bonds. This is why products are typically packaged in opaque bags. With respect to the air, it contains oxygen, and this provides an oxidizing effect. When we heat up an elastomer in an oven, what we are effectively doing is oxidizing it, and the temperature is just making that chemical reaction occur quicker. If we were to do the same test, but in a nitrogen environment, the properties of the material would remain unchanged. So what does all this mean in the real world? Well, let's try and look at a real-life example. Here, an application calls for a material to have 4 industry approvals. We can see there's 2 from the NORSOC M710 and 2 from API 6A. When we look at the temperature, pressure, test media, the sample geometries, the sample compression, and the actual test times, we can see a wide variation across the 4 approvals. The material is going to be used in a subsea Christmas tree, and you can see the design temperature, operating pressure, the media, the geometry, and the seal life are massively different to those listed in the approval programs. In the bottom matrix we can see an option of 5 different material families. Nitriles. On paper this would fail the test based upon the temperatures that are required for NORSOC M710 Revision 2 Annex A. However, if we were to simply reduce the temperatures, we would achieve a pass. When we look at nitrile and the API 6A test regime, it will fail due to a combination of the high temperature and H2S content. In this case, we can't change the high temperature because it's governed by the design temperature in the application. Ultimately, we have a number of materials that gut feel would say, well, this should work. For example, FEPM, or trade name AFLAS. This would fail the NORSOC M710 Revision 2 Annex A heat aging test because of the hydrocarbon content, but this test is to test for resistance to H2S. FEPM or AFLAS is actually very good with H2S and it is the hydrocarbon content that is resulting in this failure. If we were to change the hydrocarbon content to a more benign hydrocarbon cocktail, then I'm sure that the AFLAS would pass. If we look at the HMBR example, it's achievable across the board apart from the API 6A immersion testing to FFHH. In this case, it has failed because of the toluene content. However, when we read through the standard, the hydrocarbon content is not defined and is at the discretion of the supplier. So a simple change to this hydrocarbon oil phase would be to move it to kerosene or diesel oil. You would achieve a pass. So by careful selection of what the test criteria is, can have a huge effect on whether a material passes or fails. When selecting the test criteria, please make them relevant towards your application. In this case, you can see the application media is produced fluids, composition is unknown. We then have control fluids, corrosion inhibitors and seawater, yet none of the industry approvals take these media into account. In summary, use datasheets as a tool to help define a short list of material candidates which may or may not be suitable for your application. If there is information missing or you require further validation, speak to your supplier, they should be able to help you with this. When it comes to testing, make sure that all the details are fully defined, whether that's with respect to the method or the criteria. For example, how pressure is applied or removed can be crucial in terms of the influence on the results. If you can understand the possible root causes of the failure modes that might be associated with a particular application, it can go a long way to eliminating material candidates or actually promoting material candidates. This can be invaluable. In short, think of datasheets like brochures from a car showroom. Yes, you can go and visit the car showroom from various suppliers, get different brochures, have a look through, you read through the text, but ultimately going and test driving a car, speaking to the supplier of that car will help define whether that car is right for you or not. Thank you for listening. I hope this webinar has been of some value to you. We'll move on to the questions now. Thank you.